50-ish supernovae. Now we have 1,050 supernovae. So we've really kind of gone from here to here. Just quite a big jump. But as I'll say in a little bit, this is kind of nothing compared to the jump that we're about to take. So going from here to here, basically what that gives you in cosmology space is the original discovery of dark energy is this black contour here. And then what I get using the most up-to-date and best calibrated sample is Pantheon here. So this almost makes it seem like science is too straightforward, that we just have kind of been narrowing down the contours. So there's, I think, a little bit of luck in how perfectly centered this.
Is it 1 sigma?
So this is 1 and 2 sigma, and then kind of dark is 1 and 2 sigma. Yeah, there. But it's really been amazing progress on the wave 1A front. Now with Pantheon, this places the best constraint on dark energy to date, and we get equation of state of dark energy of minus 1.026 plus or minus 0.041. So 4% measurement of dark energy, this is right now totally consistent with the cosmological constant. So what kind of got us excited originally with our first pan-search results is maybe there is a little less than 2 sigma away from W minus 1. Now we've done a kind of much better job on several fronts, and what we see is something very consistent with the cosmological constant with a very small uncertainty.
Yeah. There is this discussion about the Hubble constant not being consistent between CMB and the rest.
Yes.
So why doesn't it impact on, are you marginalizing over H0?
I'm marginalizing over H0.
But
yes.
In principle, if you were to ask, there would be some inconsistency, right?
Yes. So let me get to this actually in the next slide. Okay. So this is about W versus H0. So maybe this will try to answer a bit of what you're asking. Okay. So the measurement of W, or sometimes people use Q0 as kind of like the second order expansion of the Hubble diagram. So for W, really what you're doing is you're comparing supernovae at Z of 0.05-ish, kind of supernovae here to supernovae here, Z of 0.5. So that's supernova, that's for W. And really the measurement that you're trying to make, what's so hard about it is that it's about a 1%. You're measuring kind of relative to your best fit, to some cosmology, the uncertainties are about 1% here compared to here. And what's especially tricky is that you're going through a lot of the universe to make this detection. So for supernovae here compared to here, there are different kinds of galaxies. You're using different samples to measure them. A lot's changing. For H0, really, kind of for the size of the Hubble constant tension, what we're doing is we're comparing supernovae here, basically what we call the calibrator supernovae, all the way here to supernovae here. Now, for me, the H0 measurement is much simpler and easier than the W measurement, because this is a 4% measurement when you are comparing two parts of your Hubble diagram that are very close in redshift space, where you have the same samples, similar galaxies, just much easier. Whereas for W, it's 4 times harder over a much bigger parameter space. Now, for W, what we do with H0 is basically we say, okay, all we're really doing is comparing these supernovae to these supernovae. So essentially you marginalize over H0. And in that sense, the supernovae by themselves don't really say anything about the Hubble constant tension. You need kind of what we have in the local distance ladder. You need something to anchor the supernova distances. Or else basically, you could just move this line up or down, and the supernova, the H0 is degenerate with the luminosity, the absolute luminosity of supernovae. So they can't say one way or the other anything about H0. It's only after you tie it to something else that you can. And so in the luncheon talk, I'll talk more about kind of problems with the H0 measurement, possible problems with the H0 measurement from supernovae, and kind of what the latest gossip is. Okay. Any other questions about that? All right. So this so far has been kind of the traditional way of putting together a supernova Hubble diagram, where a supernova goes off and you get a spectrum and you say, okay, this is definitely a Type Ia supernova, and here's this redshift, and then it goes on this Hubble diagram. what's happening now is that we're moving away from this kind of normal, traditional thing, and we're having these photometric samples. So this is the Pan-STARRS Medium Deep Survey, which has discovered the largest amount of supernovae, but what it doesn't have is we're not sure about what type the supernova was and what the redshifts of those supernovae are. So this histogram here, basically the blue is everything that we get spectroscopic confirmation of, and the gray is everything that we think has gone off and we're using photo-Z's to figure out the redshift. And you can see that we're basically now at something like 5 to 10% of all the supernovae that we measure do we have, are they spectroscopically confirmed. So this is kind of from a big program led by the CFA using hectospec. And so that's where we start getting the redshifts for these galaxies. But this is really kind of a totally different way of doing it, where you want to use the gray, but you're not sure if you have the right kind of supernovae or not, and you try to, after the survey is done, you try to go and get all the host galaxy redshifts. All right, so what this looks like, this is another Hubble diagram, and at the bottom here, this is the low redshift sample. This is all kind of a past sample. But then high up in the Hubble diagram at higher redshifts, what you can see is in purple all the supernovae that make it into the photometric sample, and in orange these are the spectroscopically confirmed supernovae. Now your eye should kind of pick up that a lot of the purple, basically what's in the photometric sample, does fall roughly on your best fit cosmological model, but you have lots of contamination. And the really hard part is trying to figure out now what to do with all this contamination. And can we do better with the light curves to try to get rid of more of this contamination? So there's this process is being tackled in multiple ways. One, we're trying to figure out what this contamination is. Then we're trying to, from the light curves, come up with better machine learning classifiers to get rid of this, to get rid of all this contamination. And then we say, okay, well, we're going to have some left over, and let's marginalize over it and see how bad of a problem it is. Okay, so how bad?
Sorry, spectroscopic is more reliable than photometric, right?
Yes, yes.
So why don't you just disregard them?
Yeah, so the problem is that, so if we could, we would use spectroscopic for everything. But the problem is that to get a confirmation, this takes an hour on a big telescope. And now that we're in the thousands for supernovae, we just can't get that kind of time anymore. So no TAC for a telescope will allow us enough time to start to classify all these supernovae. So this fraction, which is 5 to 10-ish%, has just dropped in every consecutive supernova survey. So for LSST, as I kind of say, this fraction is going to be way less than 1%. We just don't have the resources to confirm all the supernovae. So we would want to do this with spectroscopy, we just can't. There's just too much sky and too many supernovae going on. Okay. All right. So how bad of a problem does this seem to be? Well, what we can do is we can say, all right, well, let's treat this full photometric sample like a normal Type Ia supernova cosmology analysis, and we kind of will curate the data like we normally do for Type Ia, and that basically if we put in some cuts saying this is what normal Type Ia supernovae look like. So if you start with something like this, after a typical Type Ia supernova cuts, just for the quality of the light curves and kind of how normal they look, it ends up like this. So you say, okay, let's do our normal cuts like we were doing anything else, assuming that these are just 1As, and then we do this thing called beams, this Bayesian estimation applied to multiple species. So we say, all right, now we know there's contamination, so let's put some Bayes prior on the contamination and the 1As, so basically two different distributions, and we'll marginalize over the contaminating distribution, and you get cosmology. And what's so exciting about this is that when we do this, we see a systematic about 1%. So what I'm saying is, right now we're at about a 4% uncertainty for our best measurement of dark energy. This systematic seems to be 1%. So as far as we can tell, this is not limiting kind of how well we can measure dark energy. And this just...
So this beams magic.
Beams magic, yeah.
It's more than just looking at the points and saying, I don't like these points.
Yeah, right. So
how can you do better than that? What is it doing?
Right.
Because it's like throwing the baby with, how do you know that you're not throwing the baby with the
Yeah.
bath?
Right. Yeah, great question. Right. So so basically, we have these different light curves. Let me just go all the way back. Yeah. Okay. So this is what these are what Type Ia supernova light curves look like. And so we have these classification algorithms that say, all right, this is what a normal Type Ia supernova light curve looks like. Now, for core collapse supernovae, they don't look like this. Like there's two P's that they have a plateau. We can say, all right, this very much does not look like a 1A. So we'll give that we'll assign that a lower probability to be a 1A. So kind of part of this, what I'm calling Beam's magic, is you have from some classification code assigned probabilities saying what's mostly in the contamination are getting low probabilities of being 1As anyway. And then, so every supernova on here gets some possibility that it's a 1A and possibility that it's core collapse. Right.
So then,
Yeah.
how bad is the problem with 1Cs?
How about what?
How bad is it with 1Cs?
Oh, right. So yeah. So there's different types of supernovae. So there's kind of core collapse, which so there's type 2s, which don't look so much like 1As, and then there's 1Cs, which I just mentioned, which look a lot more like 1As. So it turns out from what we've seen that 1Cs are just as bad as type 2s, and it's only because while 1Cs look more like 1As, there's just less of them. So and really what's killing us is that when we start pushing into low signal to noise, then it's hard to discriminate anything. So we do have 1Cs that are sneaking in kind of on the bright end, and that's unusual. I mean that's unique to 1Cs. But for the most part, where we're struggling is just as we push into low signal to noise, and then we can't do any classification. But it seems to be equally problematic between type 2s and 1BCs.
And you're sure the source